Students, today we are going to do problems on time response analysis. Okay, so here the problem is given. So we are going to do problems on time response analysis. So here the problem is given. Any unity feedback system is characterized by an open loop transfer function. Okay, this is open loop transfer function. So I have connected a unity feedback system, that is h of s is equal to 1. Okay, so this feedback is characterized by this an open loop transfer function. So gs by h, k by s into s plus 10. So we have to determine the gain. So gain of the system. So what is the open loop transfer function equation they given? G of s by g of s is equal to k by s into s plus 10. So we have to find the gain k, and also so if the system damping ratio, they have given system damping ratio they have given as 0.5. system damping ratio 0.5. so what we have to find? We have to find the damping ratio of 0.5 for k, for this value of k. For the k value, how much they given? Damping ratio 0.5. What you have determined the peak overshoot? So determine the peak overshoot, and also time at peak overshoot for unit step signal. Okay, so we have to find out this one, maximum peak overshoot and peak time. We have to find. Okay, time at peak overshoot we have to find it. So this one, so this is a response. So you have to find this maximum peak overshoot and also peak time. So this is the peak time from here to here. This one is the peak time. So these two parameters along with the gain you have to find it, right? So we know what is the transfer function they have given. The transfer function they have given, the transfer function, you know, C of s by R of s. C of s by R of s is equal to, so G of s by 1 plus G of s into H of s. G of s into H of s. We know that feedback is a unity feedback. Okay, it means here H of s is equal to 1. This is a unity feedback. So you just substitute here C of s by R of s is equal to, what is our G of s? G of s is k by s into s plus 10 by 1 plus k by s into s plus 10, right? H of s is equal to 1. So when you take LCM, so what do you get here? C of s by R of s is equal to, so what do you get? K by, so you will get k by s into s plus 10 plus k. So this equation you will get, this is the transfer function you will get. This is a closed loop transfer function. Okay, so you can elaborate this one. C of s by R of s, C of s by R of s is equal to k by, so what happened, this one, s into s square plus 10s plus k. This is a k value. Okay, now the value of k can be evaluated by comparing the system transformation with the standard form of second order transfer function. So how are you going to evaluate this k value? By comparing with the standard transfer function. What is the standard transfer function? C of s by R of s. Okay, so k by this is omega n square by s square plus 2 zeta omega n s plus omega n square, omega n square. So what is, just compare this transfer function with the standard transfer function, that you get omega n square is equal to k. So omega n is equal to root k. And what is 2 zeta omega n? 2 zeta omega n is equal to how much? 10. 2 zeta omega n is equal to 10. Okay, and here zeta omega n is equal to how much? 5. Okay, so what is the zeta value? Already zeta value already is given. What is already zeta value? So zeta is equal to 0.5. so omega n is equal to 5 by 0.5. okay, 0.5. so what the value you will get? So you will get k omega n, I am going to write like this, omega n is equal to 5 by 50. 5 by 50. Okay, I take another sheet. 5 by 550. Okay, omega n is equal to 5 into, so 10 by 5, 5 1 ja, okay, 5, just you will get only 10. So omega is equal to 10. So you have already know omega n is equal to root k. So when you substitute here, omega n is equal to, so here if you substitute omega n is equal to 10 in this place, so you will get 10 k. So what is the root k? Bring the square this side, it become 10 square. Okay, so k is equal to 100. K is equal to 100. So we have to find maximum peak overshoot and peak time. Okay, so you know that this is the response. So this is the response. We have to find this maximum peak overshoot, and this is the peak time. So TP you have to find it. Okay, so how we are going to find it? So what is the equation for percentage of peak overshoot? Okay, so here we have to find here percentage of peak overshoot and peak time. So first I'm going to find percentage of peak overshoot. Okay, so the percentage of peak overshoot, so the formula is percent of MP, m suffix p, so e raised to minus zeta 5 by root of 1 minus zeta square into 100. So you just substitute here, percentage of MP is equal to, so zeta is equal to how much? So zeta value is minus 0.5, pi means here 3.14 by root of 1 minus 0.5 whole square, okay, into 100. Okay, so if you just calculate this one, so you will get 0.163, okay, into 100. It means here 16.3 percentage. Okay, so maximum peak overshoot is 16.3 percentage. It means this value. So this value is how much? This maximum peak overshoot is 16.3 percentage. We have to find the peak time. So to find the peak time, so what is the equation for the peak time? So peak time Tp is equal to 5 by omega d. Okay, so you know that omega d is equal to omega n root 1 minus zeta square. So what is the pi value? 3.141 by omega n, how much? 10. Omega n is equal to 10. Then root 1 minus 0.5 whole square. So you will get, if you just use the calculator and find, you will get the value 0.363 seconds. So Tp is equal to 0.363 seconds. So I'm going to write the result here. So the result is the value of gain k is equal to 100. Okay, then percentage of peak overshoot MP is equal to how much? It is 16.3 percentage. Okay, and the peak time so that is a TP is equal to 0.363 second. So these are the result. So we'll do another problem. So another problem is a unity feedback control system. So I'm just going to write a unity feedback control system. If unity has an open loop transfer function g of s is equal to 10 by s into s plus 2. What you have to do? Find the rise time. Then percentage overshoot, peak overshoot, and the peak time, and the settling time, for a step input (12 units). Step input is 12 units. So what you have to find? So the problem. So unity feedback control system has an open loop transfer function, same like the unity feedback control system. So this is g of s. Okay, this is g of s, and it's a unity feedback. Okay, here h of s is equal to 1. So this is r of s is equal to 12 units. Okay, this is c of s. What is the characteristic equation for this? 1 plus g of s is equal to 0. Okay, so from this characteristic equation, so we have to find, actually what you have to find, a rise time. TR we have to find, and also we have to percentage of maximum peak overshoot. Okay, and also you have to find settling time TS. Okay, you have to find the settling time, and also you have to find the peak time TP. Peak time also we have to find it. Okay, so we have to find the rise time TR, we have to find MP, maximum peak overshoot, and also we have to find peak overshoot for 12 units. Okay, and also peak percentage MP for 12 units you have to find. Okay, and another thing you have to find peak time TP and settling time TS. So these are the things we have to find it. Okay, so here from unity feedback control system, so the closed loop transfer function, the closed loop transfer function C of S by R of S is equal to G of S by 1 plus G of S. So here H of S is equal to 1. Okay, if we substitute your G of S, if we substitute here G of S is equal to 10 by S into S plus 2. So substitute here. So what do you get? C of S by R of S? C of S by R of S is equal to, so after substituting you will get 10 by, okay, S square plus 2S plus 10 you will get. Okay, so now compare this equation with the standard second order system. What is standard second order system? Omega n square by S square plus 2 zeta omega n S plus omega n square, right? Here omega n square is equal to how much? 10. Okay, then 2 zeta omega n is equal to how much here? 2 zeta omega n is equal to 2, right? Here from this equation omega n is equal to root 10. It means omega n is equal to, this value become 3.162 radians per second. So this is omega n value. Okay, from this equation, so 2 zeta omega n is equal to 2. Okay, then here 2 gets cancelled, so zeta is equal to, right, 1 by omega n. So what is the omega n? 3. So that value is 3.162. So omega, so zeta you will get 0.316. So zeta is equal to 0.316. Zeta is equal to 316. Okay, now from this equation, so rise time, what is the rise time? So rise time, I have to find first rise time. Rise time TR you have to find. So rise time TR is equal to, what is the equation rise time? So rise time equation is 5 minus d by omega d. So you know what is the omega t is equal to, you know what is the theta? Theta is equal to tan inverse 1 minus zeta square by zeta. So this is a theta value. So what is omega d? Omega d is equal to omega n root 1 minus zeta square. So if we substitute zeta value, what is the zeta value got? So our zeta value is here 0.316 is your zeta value. So if we substitute in this equation tan inverse 1 minus 0.316, right, by zeta is equal to 0.316. So you will get, this value will get 12.49 radians theta value. So we substitute in the omega n value, omega d, omega n already you know how much omega n? Omega n is equal to 3.162 radians per second, 1 minus, so zeta you know 0.316 whole square. So you will get omega d is equal to, so you will get 3 radians per second. So this is the omega d value. Okay, so we substitute in the rise time. So what is the rise time? So rise time equation is TR is equal to, and the pi value is how much? Pi minus, so 12.49 by, so if you substitute here omega d, how much? 3. Omega d is equal to 3, we substitute, so you will get finally 0.63 seconds. So your TR is equal to 0.638 seconds. 3 seconds. Next you have to find percentage of overshoot. Percentage of peak overshoot you have to find. You have to find the MP. Okay. To find MP, so what is MP? So MP equation is e raised to minus zeta omega n root 1 minus zeta square, okay, into 100. So e raised to zeta value is how much? So zeta value, you know that 0.316 into pi by 1 minus 0.316 whole square, okay, into 100. You just calculate, so you will get, so 35.12 percentage. This is the percentage of MP. Okay, then peak overshoot is equal to what? Percentage of MP into unit step. So percentage MP how much? 35.2 by 100 was, so unit step is 12 units. That's a 12 units. So how much you will get? So you will get 4.2144 units. So peak overshoot is this value. Peak overshoot is this value. Okay, so we'll find a peak overshoot. So we have find the peak overshoot. Is 4.2144 units. Now we are going to find peak time. So what is the equation for the peak time? So the peak time, so TP, peak time is, so that is a PT. So PT is equal to TP is equal to, the peak time equation is so pi by omega d. So peak time means this is the peak time. So from here to this is the peak time from this point to this much. How much time response taken to reach from this point to this peak. So that is the equation for omega by pi by omega d. Okay, so what is the pi? Pi means 3.141. Omega d, you know already, 3 radians per second. So when you divide 3.141 divided by 3, how much you will get? 3.141. So divided by 3, so you get 1 point. So you get TP is equal to So you get here 1.047 seconds. So this is the TP value. So next we have to find the settling time. You have to find the settling time. So what are the equation for the settling time? What are the equation for the settling time? Right. So the settling time equation is, right, settling time TS. Settling time is TS. You know, see, when you take the graph, so this is your input signal. So our output is tracking. Okay, output is tracking your input. Okay, so this is, I told you, error 2% or 5%. Okay, 2% or 5%. I'll take a fresh sheet and I will explain you what is this settling time. So the settling time, so we are going to find the settling time value. The settling time TS is equal to, so we have to find the settling time. How to find the settling time? You just see this one is your response signal. This is C of t. Okay, this one is your input signals, and also you see that there are bands, 2% and 5% tolerance band. Okay, you just see that if it is a 2%, it was a 2%. I'll just tell you, it's a 2%. So this is a 2%. 2% means this is the 1. 2% means 1 or 2. This one is the 99, plus or minus 2%. Okay. So this is a tolerance band. Suppose you see that your response. See, your response is like this. So it started here. You see that your response, okay, reached this point and staying within that band. Okay, that time is called settling time. Already told. Okay, so you just see that this is still above this line. It is still below this line, but here also above. But when come to this point, it is settled within the band. Okay, settled within the band. It is not going above or below. So when it reached in the 2% of tolerance band and stayed within that, so the moment which is reached, we taken as a settling time. So we have to find what is the settling time. So we are going to find the error of 2% and also 5%. Okay, so what is the formula for settling time? So we know that settling time TS is equal to 3T. So that is for 5%. That is for 5% error. And TS is equal to 4T. So that is for 2% of error. 2% of error. Okay. So that is 3T for 5%, 2T for 4T for 2%. So what is the T here? T is a time constant. Here T, this T is time constant. Time constant T is equal to, you know that, the 1 by lambda omega n. So Ts is equal to, for finding settling time for 5%. So what is the value? So we will do it here. So you know that here from this equation, Ts is equal to 3t. So it means here error here is 5%. Okay, T means you already know. T is means here 1 by zeta omega n, 1 by zeta omega n. So Ts is equal to 3 by, what is the zeta value you got? What is the zeta value? So zeta is here 0.316 is a zeta. Okay, so what is the omega n? Omega n is equal to 3.162. You just multiply, so divide, you will get, this is 1 second. 1 second you will get, right? So therefore, so this is 1 second. So how much time it is taken to reach here? It is taken 1 second. Within 1 second it is settled in a specified band. So for 2%, if we take 2%, Ts is equal to, that is 40. Ts is equal to 40 is the error percentage, 2% error. So what is the Ts? 4 into 1 by lambda omega, sorry, this is zeta omega n. Ts is equal to 4 into, what is zeta? Zeta is equal to, you already know, 0.316. So what is the omega n? Omega n you already know, 3.16t. So when you divide it, so you will get 4 seconds. You will get 4 seconds. You will get 4 seconds. Okay. Here settling time, how much you got here? So settling time is so this is a Ts by, so this value, so here is a 3 seconds. It is a 3 seconds. Okay. So here is a Ts is equal to 4 seconds. Ts is equal to 4 seconds. So when your error is 2%, here your when your settling time, when is 5% of error, so you got 3 seconds. 3 seconds. These are the values. I am going to write the result here. I am going to write the result. I'm going to write result. So what is the rise time you got? What you got rise time? So rise time, so that is Tr is equal to, you got 0.63 second. Okay. Next percentage overshoot, that is percentage MP is equal to 35.12%. Then peak overshoot, so we got 4.2144, okay, units. Next peak time, TP, so TP you got 1.047 seconds. Next settling time, that is a Ts you got 3 seconds for 5% error. Okay, and 4 seconds for 2% error. So this is the answer. Okay, so next problem I'm going to write. So a closed loop servo is represented. A closed loop A closed loop servo is represented by the differential equation that is d square c dt square plus 8 dc by dt is equal to 64e. Okay, where c is the displacement of output shaft. Okay, this one is the e. Here c is what? C is here displacement. C is the displacement of the output shaft. Okay, so there is a servo motor, so that's the servo system. Differential equation is this. So the C is the displacement of the output shaft, R is the displacement of the input shaft. R is displacement of the input shaft, and E is equal to what? E is means R minus C. Set points is equal to, this is error is equal to set point minus measured value. So R means displacement of the input shaft, C is mean displacement for the output shaft. So what we have to determine? So we have to here the question is determine. Here the question is determine undamped natural frequency. You have to determine omega n, undamped natural frequency, and damping ratio, and percentage of maximum peak overshoot for unit step input. So you have to find MP. So these three parameters you have to find for the given differential equation. Okay. So what is the solution? The solution is. So what is the differential equation? The given differential equation is C d square C by dt square plus 8 dc by dt plus 64 e. So you have to apply the Laplace transform. Before that, what you have to do, you have to apply d square by dt square plus 8 dc by dt is equal to 64. E means what? R minus C. Okay, you apply the Laplace transform. Apply Laplace transform to equation 1. So you take as equation 1. So when you apply Laplace transform to this equation, so what do you get? So Laplace transform of d square C dt square plus 8 dc dt plus 64 R minus C. Okay, so what do you get? So this will be S square, the formula is S square XC. So this will be 8S XC. So this is 64 R of S, minus C of S. Okay, actually you have to find C of S by R of S from this equation. Okay, so here, so I am going to take a common X of C. when you take a common x of c from the above equation, x of c, so when you see s square plus s is equal to 64 rs minus c, rs minus cs, okay. So here this is c, this is c of s, sorry, this is c of s, so this is c of s. So here here is not x of c, this is c of s, here also c of s, okay, here also c of s. So what happened? So now c of s is equal to s square plus s is equal to 64 into rs minus 64 cs. So 64 cs, you just bring this side, cs s square plus s plus 64 cs is equal to 64 r of s. So what is common here? C of s is a common. C of s is, when you take C of s common, s square plus s plus 64 is equal to 64 into r of s. So what is the transfer function? You know, C of s by r of s is equal to 64 by s square plus s plus 64. So you compare this equation with the standard equation. What is the standard equation? Omega n square by s square plus 2 zeta omega n s plus omega n square, Here omega n square is equal to 64, right? So omega n is equal to root 64. So omega n is equal to what here? 8. Omega n is equal to 8 radians per second. 8 radians per second. Okay. So you have to find what is the damping ratio from this equation. What is the damping ratio from this equation? So you can find the damping ratio from this equation. So when you compare this, so damping ratio from the standard, this equation and this equation, when you compare, so 2 damping ratio omega n is equal to 1. So here this coefficient is 1. 2 omega n is equal to this s coefficient is 1. So you already know omega n. So omega n is equal to 8. So 2 8 is equal to 1. So how much? 1 by 16. So what do you get the 1 by 16? The 1 by 16 value is just wait a minute. This is completely wrong. I have missed it here. 8. There is a small correction here. So you have to put here 8. Here also 8. Here also 8. Okay. Here also 8. Here also 8. Yes. 8s. So this would be 8. This would be 8. So what happened here? So 2 zeta 8 is equal to 8. So zeta 2 into so this is 8, both gets cancelled. Okay. So zeta is equal to 1 by 2. So it is a 0.5. So zeta is equal to 0.5. So you have to find maximum peak overshoot. You have to find maximum peak overshoot. The equation is maximum peak overshoot e raised to minus zeta 5 by 1 minus zeta square, root 1 minus zeta square into 100. Okay, right? So when you substitute here, you get e power minus zeta means how much here? 0.5 into 5 by root zeta means again here 0.5 whole square, so into 100. So you will get percentage of MP MP is equal to how much? It is 16.3%. 16.3%. So what is see the result here? The result I am going to write here. Result is omega n is equal to 8 radians per second. Okay, and damping ratio is equal to 0.5, and the maximum peak overshoot is equal to 16.3%. So this is answer. Next problem I'm going to write. So a closed loop servo is represented. A closed loop servo is represented by the differential equation that is d square c dt square plus 8 dc by dt is equal to 64e. Okay, where c is the displacement of output shaft. Okay, this one is the e. Here c is what? C is here displacement. C is the displacement of the output shaft. Okay, so there is a servo motor, so that's the servo system. Differential equation is this. So the C is the displacement of the output shaft, R is the displacement of the input shaft. R is displacement of the input shaft, and E is equal to what? E is means R minus C. Set points is equal to, this is error is equal to set point minus measured value. So R means displacement of the input shaft, C is mean displacement for the output shaft. So what we have to determine? So we have to here the question is determine. Here the question is determine undamped natural frequency. You have to determine omega n, undamped natural frequency, and damping ratio, and percentage of maximum peak overshoot for unit step input. So you have to find MP. So these three parameters you have to find for the given differential equation. Okay, so what is the solution? The solution is, so what is the differential equation? The given differential equation is C d square C by dt square plus 8 dc by dt plus 64 e. So you have to apply the Laplace transform. Before that, what you have to do, you have to apply d square by dt square plus 8 dc by dt is equal to 64. E means your R minus C. Okay, you apply the Laplace transform. Apply Laplace transform to equation 1. So you take as equation 1. So when you apply Laplace transform to this equation, so what do you get? So Laplace transform of d square c dt square plus 8 dc dt plus 64 r minus c. Okay, so what do you get? So this will be s square, you know the formula s square xc. So this will be 8 s xc. So this is 64 r of s, 64 r of s minus c of s. Okay, actually you have to find c of s by r of s from this equation, okay. So here, so I'm going to take a common x of c. When you take a common x of c from the above equation, x of c, so when you see s square plus s is equal to 64 rs minus c, rs minus cs, okay. So here this is c of s, sorry, this is c of s, so this is c of s. So here is not x of c, this is c of s. Here also c of s, okay, here also c of s. So what happened? So now c of s is equal to s square plus s is equal to 64 into rs minus 64 cs. So 64 cs, you just bring this side, cs s square plus s plus 64 cs is equal to 64 r of s. So what is common here? C of s is a common. C of s is, when you take C of s common, s square plus s plus 64 is equal to 64 into r of s. So what is the transfer function? You know, C of s by r of s is equal to 64 by s square plus s plus 64. So you compare this equation with the standard equation. What is the standard equation? Omega n square by s square plus 2 zeta omega n s plus omega n square. Here omega n square is equal to 64, right? So omega n is equal to root 64. So omega n is equal to what here? 8. Omega n is equal to 8 radians per second. 8 radians per second. Okay. So you have to find what is the damping ratio from this equation. What is the damping ratio from this equation? So you can find the damping ratio from this equation. So when you compare this, so damping ratio from the standard this equation and this equation, when you compare, so 2 damping ratio omega n is equal to 1. So here this coefficient is 1. 2 omega n is equal to this s coefficient is 1. So you already know omega n. So omega n is equal to 8. So 2 8 is equal to 1. So how much? 1 by 16. So what do you get the 1 by 16? The 1 by 16 value is just wait a minute. This is completely wrong. I have missed it here. 8. There is a small correction here. So you have to put here 8. Here also 8. Here also 8. Okay. Here also 8. Here also 8. Yes. 8s. So this would be 8. This would be 8. So what happened here? So 2 zeta 8 is equal to 8. So zeta 2 into so this is 8 both gets cancelled. Okay, so zeta is equal to 1 by 2, so it is a 0.5. So zeta is equal to 0.5. So you have to find maximum peak overshoot. You have to find maximum peak overshoot. The equation is maximum peak overshoot e raised to minus zeta 5 by 1 minus zeta square, root 1 minus zeta square into 100. Okay, right? So when you substitute here, you get e power minus zeta means how much here? 0.5 into 5 by root zeta means again here 0.5 whole square, so into 100. So you will get percentage of MP is equal to how much? It is 16.3 percentage. 16.3 percentage. So what is see the result here? The result I am going to write here. Result is omega n is equal to 8 radians per second. Okay, and damping ratio is equal to 0.5, and the maximum peak overshoot is equal to 16.3 percentage. So this is answer. Okay. Hello students, next we are going to do problems on steady error constant and steady state error. Okay, here is our problem is that for servo mechanism with the open loop transfer function given below. So these are the servo mechanism transfer functions. So you have to find what type of input signal gives rise to a constant steady state errors. We have to find the constant steady state errors and also have to calculate their values. Okay, we will see that one. It means you have to find what is the value of kV, and also you have to find the steady state error constants. You know that steady state error constants. So we have Kp, Kv, Ka. You have to find their steady state error constants, and also we have to find steady state errors. Okay, for their values means. Okay, we will see one by one. So in the first one, the first transfer function is A. The first one is G of S. The first one is A. So G of S is equal to, so what is that? 20 S plus 2 by S into S plus 1 S plus 3. So this is the given servo mechanism open loop transfer function. Okay, you assume that here H of S is equal to 1. H of S is equal to 1. Unity feedback system. Okay, now the open loop system has a pole at origin. You see that here you see that the open loop system is the power is 1. So the open loop system has a pole where? As pole at origin. As pole at origin. Hence, so one pole is there at origin. Okay, so we say that it's a type 1 system. Hence it is type 1 system. Hence it is type 1 system. So in system with type 1, so you will get the velocity input will be given a error steady state constant. So I will write here, this is a type C system. Okay, in systems with type 1, in systems with the type 1, the velocity or ramp, the velocity input or ramp input will give a constant steady state constant steady state error it will give. So what do you understand? See, the given servo mechanism, this is open loop transfer function. You know open loop transfer function, g of s into h of s, okay, is a loop transfer function. So the open loop system has a pole at origin. So it means s power 1 means one pole is at origin. So we say that it is a type 1 system. So in systems with the type 1, so what happened? The velocity or ramp input will give a steady state error constant. Okay, type 1 systems, so will give, okay, so error will give in constant steady state error. You see that it's already you know this diagram. Okay, already you know this diagram. So here you see that error constant, this is error constant, this is a type number system. So error constant, okay. So what is the type of signal you get? So in this here, if you just see here, yes, here. So for the type 1 system, this is a type 1 system, okay. For the type 1 system, so what is input here for type 1 system? What is input signal? It's a ramp signal. That's what I told you, it's a ramp signal, okay. So what is the steady state error with the unity velocity input? That is ESS by K. So I am writing here. So the steady state error with unity feedback. What is it? Unity feedback. Sorry, the steady state error with unity velocity error. Okay. So what is that? ESS, you know that ESS is equal to 1 by kV. Right. When type 1 system is subjective, when type 1 system means, see this type 1, it's a type 1 system. So when you get the steady state error, when your type 1 system is subjected to a ramp signal, so you will get, so your its error constant would be here 1 by kV. Okay. Now we find a velocity error constant. So what is the equation for velocity error constant? Velocity error constant. Velocity error constant is kV is equal to limit, you know this equation, kV is equal to limit s tends to 0, then s into g of s into h of s. You know this equation. I have given equations for velocity error constant, positional error constant, accelerator error constant. I have given all the equations. Okay. So so you have substitute here, kV is equal to limit s tends to 0. So what is our g of s? So g of s is equal to 20 into s plus 2, 20 into s plus 2 by s into s plus 1 into s plus 2. Okay. So this is your open loop transfer function. Okay. So now what happened? ESS gets cancelled. So after that you have to substitute s, limit s tends to 0, substitute s tends to 0, 20. So this will be 0 plus 2, 0 plus 2, so 0 plus 1, okay, 0 plus 2, so much you will get 20 into 2 by 2. So you will get, so the value is kV value is 20. Sorry, here this value is 3, it's not 2, so this value is 3. So you will get, this is a 3, this is a 3, okay, how much here, 40 by 3, so you will get 40 by 3. So your kV is equal to here 40 by 3, kV is equal to 43. So you got, so velocity error constant. Then after that you have to find the steady state error. So you know that what is the steady state error? Steady state error, okay, steady state error. So that is ESS is equal to 1 by kV. You know this formula, kV. So what is that here? 1 by kV means 40 by 3. 40 by 3 means how much here? So this is 3 by 40 is equal to 0.0.075. So your kV is equal to your ESS, steady state error, is equal to 0.075. Okay, then again another transfer function is given. Another transfer function. What is the second transfer function? So what is the second transfer function? Second transfer function is g of s is equal to 10 by s plus 2 into s plus 3. So this transfer function g of s is equal to 10 by, okay, s plus 1 into s plus 10 by s plus 2, see s plus 2, s plus 3, s plus 3. Of course here also h of s is equal to 1, h of s is equal to 1, right. So now see that the open loop system has no pole at origin. See this open loop system, no pole at origin, right, okay. So here no, so how we determine the type number? So when number of poles are locating at origin, okay, here is, it means nothing is there to s power 0, it means no pole is at origin. So this is a type 0 system. So in systems with type number 0, the step input will give a constant steady state error, okay, so that we have to understand. So the here I am going to write the open loop, here the open loop system has no pole at origin. So here no pole at origin, s power 0 means no pole at origin, hence it is a type 0 system, okay, it is a type 0 system. So you understand, so for type 0 system, so what type of the input, okay, will give a constant steady state error. We already derived all this equation. You just see that here, this is a type 0 system. You see this table, what is the heading? Steady state error for various type of inputs. So now type 0 system, this is a type 0 system. With the type 0 system, so what happened? Your input is unit step input, okay, unit step inputs. Then what is the error constant? The steady state error, constant steady state error is 1 by 1 plus kp. This is the value, okay. So you write here, in systems with type number 0 in system with the type number 0, the step input will give a constant steady state error. I have already told you. So if you take a type 1 system, this is a type 1 system. When type 1 system is subjected to step signal, so you will get your response would be like this. You see that there is a steady state error gap is there. This is steady state error. So this portion, this gap is called steady state error is equal to 1 by 1 plus Kp. Okay. Your constant steady state error is 1 by 1 plus Kp for type 1 systems. That's the meaning of that. So now what we have to find? We have to find the Kp value. We have to find the Kp value. After finding Kp value, so you substitute in this error. That's all. Okay. So now we find the Kp value. So how to find the Kp value? So you know that position error constant. The steady state error with the unit step input is 1 by 1 plus Kp. You know that one. Okay. The steady state error, as I said here. So the steady state error for step input is 1 by 1 plus Kp. Okay, I'm going to write here. The steady state error, okay, with unit step input ESS is equal to 1 by 1 plus Kp. You know this. So I have mentioned here this one, right? This graph. So we just find the Kp value here. Kp is a position constant. Kp means position error constant. That is Kp. You know that limit s tends to 0, g of s into h of s. H of s is what? 1, since it is a unity feedback. So what is the Kp limit s tends to 0? What is our transfer function? So your transfer function is here 10 by s plus 2 into s plus 3. So 10 by s plus 2 into s plus 3. Now directly we substitute limit s tends to 0, 10 by 2 into 3. So how much you will get? 5 by 3. You get 5 by 3. So our Kp value is equal to 5 by 3. So now we have to find the steady state error. So we have to find steady state error. So what is steady state error? So ESS, your steady state error. The steady state error ESS is equal to 1 by 1 plus Kp. Right? So we substitute here. What is the Kp value? Kp is equal to 5 by 3. So you will get ESS, you will get here 0.375. I'll let it here. So ESS is equal to 0.375. So this is our steady state error. Okay. So we will see third one. We will see third transfer function. You know that g of s is equal to 10 by s square plus s plus 1 into s plus 2. Of course, this is h of s is equal to h of s is equal to 1. Okay, so now you see that the open loop system has two poles at origin. S square means s square, it means two poles at origin. It means it is a two poles at origin, hence it is a type 2 system. Hence it is a type 2 system. So in type 2 systems, in systems with the type 2 the acceleration input will be a constant steady state error. Just see that. So you have to find what type of error signal that is. So you see that this is already I have given this in this. Okay, so what is your type 2 system? Where is the type 2 system? This is the type 2 system. So for the type 2 system, so this is the, so your input signal is what? Your input signal is unit parabolic, means accelerated signal. And what is steady state error? ESS is equal to 1 by what is that? 1 by KA, 1 by KA. Okay, so that you understand. Okay, so I am going to write it here. The steady state error with unit acceleration input, the steady state error with unity acceleration input. So what do you get? ESS is equal to 1 by KA, 1 by KA. Okay, 1 by KA you got. So then what is the acceleration error constant? You know that acceleration error constant. So ESS is equal to what? Acceleration error constant. So that is KA, sorry, it is a KA is equal to, so you will get limit s tends to 0 s square g of s into h of s. You know this equation, right? So from this equation we have to find it. So KA is equal to limit s tends to 0 s square, so g of s into h of s. You know our h of s is equal to unity feedback. Okay, this is a unity feedback system. Okay, unity. So what is your g of s? You already given in the problem. K is equal to KA is equal to limit s tends to 0 s square. So your g of s is 10 by s square plus s plus 1 into s plus 2. Okay, s square gets cancelled. Now we substitute limit s tends to 0, 10 by 1 into 2, so that is how much you get? 5. So your KA is equal to, so that is a 5. Okay, so your acceleration error constant KA is equal to 5. So then what is steady state error? So steady state error ESS is equal to 1 by KA. 1 by KA means 1 by KA is equal to 1 by 5, so 0.2. So ESS is equal to 0.2. So what are the results? I am going to write it here. So the results I am going to write it here. What are the results? Okay, so results is In system, the result is the first one. In system A with the unity velocity input, the steady state error is 0.5. So I will take another sheet and it will be easy to write. Okay, so the result I am going to write it here. One in system A with unit velocity input, the steady state error is equal to 0.075. You know that. Next, in system B, question number B, with unit step velocity means here ramp. Velocity means here ramp. So unit step input, your steady state error ESS is equal to 0.375. Okay. So next to 3, in system, so with the unit acceleration is parabolic acceleration input, so your steady state error is equal to 0.2. Okay. So we will see the next problem. Next problem we are going to do it. So the next problem is, this is the next problem. So what is the problem? It says, for a unity feedback control system, the open loop transfer function g of s is equal to 10 into s plus 2 by s square plus s plus 1. Find the position, velocity, acceleration, error constant, kp, kv, ka values you have to find for a given unity feedback. Unity feedback means h of s is equal to 1 and they give open loop transfer function. So for this you have to find the position, velocity, acceleration constant. And the second part is the steady state error when input is r of s, where here r of s is equal to 3 by s, the input signal 3 by s minus 2 by s square plus 1 by 3 s square. So you have to find here kp, kv, so kp, kv and ka, and finally you have to find steady state error. Steady state error ESS you have to find it. Kp you have to find, kv you have to find, ka you have to find, and the steady state error how much you have to find it. Okay, so we just do it here. We do it. So what is here g of s? What is g of s? What is g of s? You know the g of s is equal to you know 10 s plus 2 by s square s plus 1. Since it is unity feedback, that is h of s is equal to 1. So you are given r of s, input signal is rs is equal to 3 by s minus 2 by s square, okay, plus 1 by 3 s cube. We have to find, first problem we have to find what is ka, proportional position error constant, and next we have to find kv, velocity error constant, and we have to find acceleration error constant. In the second problem we have to find steady state error. This values you have to find. You know what is a ka? What is a ka? Okay, so we'll just, I'm going to write for a problem to find static error constants. So these are the static error constant. So what is the ka? Ka means this is position error constant. Ka means here what? Position error constant. Position error constant, that is kp is equal to, what is the equation you will get? So Kp is equal to limit s tends to 0. Okay, so g of s into h of s, g of s into h of s. So h of s is actually unity feedback. So limit s tends to 0 into g of s you will get. Okay, so what is the g of s? So what is g of s? G of s, 10 by 10 into s plus 2 by s square plus s plus 1. Okay, so I'm going to take another sheet here. Okay, so what is it here? K proportional constant, that is Ka. Ka is equal to, so limit s tends to 0 g of s into h of s. So I have told you this is a unity feedback, so this become 1. So Ka is equal to limit s tends to 0 g of s. So I'm going to write, so I'm going to send limit s tends to 0. What is g of s? So you know that 10 into s plus 2 by s square plus s plus 1. Okay, so when you send inside 0, so what happened? This become, so what happened? 10 0 plus 2 by, okay, 0 square 0 plus 1. So this whole term is multiplied by, so divided by 0. So what happened? This become, so 10 into 20 20 0. So this is infinity. So now you got your proportional, your steady state error, proportional error constant is infinity. So Ka is equal to infinity. Okay, then you find what is the Kv, velocity error constant. So you have to find Kv, that is velocity error constant. So velocity error constant, limit s tends to 0 s into g of s into h of s. So h of s is equal to here 1. So I'm going to write limit Kv is equal to limit s tends to 0 s into g of s. G of s is what? G of s you already know, 10 into, so s plus 2 by s square plus s plus 1. So 1s gets cancelled here. So what you get? 10 in limit s tends to 0 10 s plus 2 by, okay, s into s plus 1, s into s plus 1. So if you substitute limit s tends to 0, so what you get? So if you substitute here, so you will get if you substitute 10 into 2 by 0, again you will get infinity. So it means here your Kv also infinity, or Kv value also infinity, velocity error constant also infinity. Okay, so next we see, we will find Ka, we'll find the Ka. So acceleration error constant Ka will find, this is Ka means acceleration error constant. So that is what? Ka is equal to, limit s tends to 0 s square g of s into h of s. So you know the formula for Ka. Okay, so what here also, h of s is equal to 1. So this Ka, so Ka is equal to what? Limit s tends to 0 s square. What is g of s? G of s, you know that 10 into s plus 2 by s square into s plus 1. So h of s is a 1. So s square gets cancelled. So Ka is equal to limit s tends to 0. So 10 into s plus 2 by, so s plus 1. When you substitute s tends to 0, so what you get? So you get 10 0 plus 2 by 0 plus 1. So that is 20 by 1. 20 by 1. So your Ka is equal to 20. Or Ka is equal to
20. So this we find all static error constant. Okay, so Ka is equal to, Ka value become infinity, Kv value become infinity, and Ka this is acceleration error constant. So this is a Kp, this is not Ka, this is a Kp. This is a Kp, this is a proportional constant, this is a Kp. Here also make a small change, here it's a Kp. Okay, so next what you have to find? You have to find steady state error for the given input. You have to find steady state error for the given input. Okay, so we will find steady state error for the given input. So second question, B part. B part, we have to find steady state error, ESS. Okay, so what is the error signal? The error signal here, the error signal in S domain. The error signal in S domain, ESS is equal to, you know that, R of S by 1 plus G of S into H of S. Okay, so what is the R of S here? So you have given R of S is equal to, so 3 by S minus, okay, 2 by S square, okay, plus 1 by 3 S cubed, 1 by 3 S cubed. So what is steady state error? You have to find steady state error ESS is equal to limit S tends to 0. Steady state error ESS is equal to here, so limit in time domain t tends to infinity, so E of t, when you convert into in S domain, limit S tends to 0, S into E of S. Okay, you take this formula, so ESS is equal to limit S tends to 0, S. What is E of S? E of S means here R of S by 1 plus G of S into H of S. You know R of S, this value is R of S. You know G of S. G of S is a transfer function, you know, that is 10 into S plus 2 by S square into S plus 1. So your H of S is equal to 1. So you substitute all the values, so you will get steady state error. Okay, so we will see this. So here what you get here, just substitute. After substituting, so ESS steady state error, ESS is equal to, you know that ESS is equal to limit S tends to 0, S into R of S by, so 1 plus G of S into H of S. Okay, so ESS is equal to limit S tends to 0. Okay, so yes, what is R of S? R of S, you know, the R of S is equal to 3 by S minus 2 by S square, okay, plus 1 by 3 S cubed. Okay, so what is your 1 plus G of S is equal to, so that is 10 into S plus 2 by S square plus S square into S plus 1, your H of S is equal to 1. Okay, so now, so what you will get? So after you mathematically you derive, so you will get 1 by 60. You will substitute all the values, so you will get 1 by 60. Okay, so here we have applied your steady state error, final value theorem you have applied. After that you got steady state error, this one, so you know very well that one. So I can do it in mathematics. Here ESS is equal to, so you will just multiply inside the s term. So finally you will get like this, limit s tends to 0. You just manipulate all the things. So this value 3s square, okay, plus s plus 1 by s square into s plus 1 plus 10 into s plus 2, okay, minus 2s into s plus 1 by, so s square s plus 1, okay, plus 10 into s plus 2, okay, plus s plus 1 by s square s plus 1 plus 10 into s plus 2. Okay, you substitute. So what happened? If you substitute s tends to 0, so what happened when you substitute s tends to 0 here? So this value become this s square here, s square will gets cancelled. Okay, here also 1 s is there, here also s square, so 1 s. So what happened when you substitute here, that value become 0, okay, this term become 0, okay, and last you will get 1 by 60, 1 by 60. So the answer is 1 by 60. So ESS here, ESS is equal to 1 by 60.